All right, welcome back. So we are looking at the main physics of eddy viscosity models and turbulent boundary layers, which are incompressible. Two-dimensional flows are really 3D, but two-dimensional mean flows, and we'll go from there. And we kind of left off mid-class, I think last Thursday, and I guess in these two classes coming up right here, I really want to get through as much of this handout as we can so that we can move into some of the quick review for algebraic models, and then we'll look at probably the Cebeci-Smith model first, which is the first huge practical model for turbulence modeling. Anyway, if you recall from last time, we were looking at molecular analogies, and just remember, a molecular analogy is not like one-to-one with turbulence. Turbulent flows where the fluctuations of the velocity components are small compared to the eddy motions. So coming back here and looking at equation 312, I believe, and remember 311 right here. We're going to be referencing this a few times in the next few classes, which is Prandtl's length model, which goes as the density times the length squared, which should be some kind of distance to the wall. We'll look at that, what that should be, times the magnitude of the velocity derivative times the velocity derivative. This was taken at a magnitude to try and force the correct sign to balance the equation. So looking at 3.2, we're looking at this little particle analogy, and if you make some kind of assumption, which is a good one for turbulent flows over a boundary layer, that v prime is on the order of u prime, then you can write equation 312. And and this comes from 311, by the way. So these particles, if they're going through a system from, say, point 1 to 2, they'll bring some so-called defect in the momentum, and that rate will go as rho times rho prime v prime. And just a few observations about this. This means that the mean is negative when du dy is greater than 0, and therefore it's possible to write equation 3.11, and that's a note about the sign. So the absolute value, which I just noted, is necessary to define the direction of the stress. So from equation 3.7, let's just go back and look at that quick. Where's my equation 3.7? Right here. Here's Prandtl's definition. Using that analogy, we can write that the eddy viscosity would go as a mixing length as L squared times the magnitude of du dy. Now, this is nice, but it didn't help too much practically. And von Kármán picked up the work in 1931, which, as you know, was Prandtl's student in Germany before he came to the United States. And he was interested in flows and pipes, much like Osborne Reynolds. And he wrote a little quote, which I pulled out, and this is translated from German. He said, "We assume similitude of the oscillatory state, irrespective of the location of the point in whose vicinity the oscillation is examined." And so what did that mean? Practically, that meant that the vorticity transfer equation in conjunction with Taylor's Taylor's series the main result will be considered by Taylor series alone. Okay, so we're going to take u of y here and expand it in terms of a series for parallel flows within pipes following von Kármán. So here we go. U of y goes as u as some point y, well, expanding about y naught, plus higher order terms. Hot. So we would assume that the flows are self-similar if they're laminar or turbulent, at least in the fully turbulent region and near the wall. That's true, and we'll see that breaks apart as we get farther away from the wall in these little chapter 3 of major flows. So we'll say that they're self-similar and they would scale as some length and velocity, and then we can take 314 and try and make it invariant of the flow size with respect to the y direction. And we'll non-dimensionalize it with u naught and L, which are right here. There's L and u naught. So we take 314 and just non-dimensionalize that way. And then we can say, well, if we don't know the scaling factor because it might be self-similar, but maybe something about the velocity profile, then one approximation of L obtained by von Kármán is K, von Kármán constant of partial u, partial y, all over partial 2u, partial y squared. And here I wrote x, and it was x in a different paper, and I tried to make it consistent by writing kappa. And that's known as von Kármán's constant. We'll look at a few values of that graphically in a few experiments later. So that's nice, and these are just like first approximations, and they were done without any like insight into high quality turbulence measurements. And we'll see how we have to just modify these basic closures to approximate something that's closer to a turbulent boundary layer with zero pressure gradient. And I've noted that here in words that these models, if they're used for pure closure, aren't totally reproducing what we would see in measurements or, with contemporary CFD. So for an example, if we have a laminar flow and there's a particular velocity that, and you might look at as, well, I guess in a laminar flow, I'll just write that there's no fluctuations, of course, if it's steady. And these arguments were based on molecular analogy. And in the molecular analogy, that the particle velocity c bar are much higher than, say, u bar, the flow velocity. But in the turbulent flow, at least the ones we're going to consider, u prime is much, well, I want to say much smaller than u bar, if on the order of like 10%. And so this is sort of a little switcheroo in terms of the analogy, which isn't great. Now, each of these relations we developed in 3.7 to 3.11. Let's just go back and remind ourselves what those are. So see, we have basically relations between our Reynolds stress and our length scales and our velocity to close the model. So that'd be like the extra term to close the model. So all those types of models have empirical coefficients, right? So if we make a turbulence closure, we have empirical coefficients. And so this is like the first time, I guess, in the class where we've really encountered some basic closure schemes. This is a basic differential equation, one equation type model, and it has extra coefficients. And you might say, well, how do we go about finding them? We might make a prediction and calibrate them and match the prediction to our measurement and then just let the coefficient be set. Or we could try and use theory and find them, and maybe they'd be more general. So those are typically the two ways to find them. And before we kind of go down that path, I want to look at figures, which I inserted 313 and 314. And they show this eddy viscosity mixing length distributions. And from, I think, some experiments here of Klebanov. There they are, very famous set of boundary layer experiments. So let's look at the first one. So this is 313, and it's dimensionless eddy viscosity. So that's epsilon m right there, normalized by Utah times delta. And the x-axis is the distance from the wall. So just, it's always, I know this newer people outside the fluid sometimes in this class, so I just draw it. Here's your velocity profile. And then this distance is y over delta, right? So you can see very close to the wall, we have 0 and 0, which is good. That makes sense. And you can see in the simplest model that when you're really close to the wall in that like viscous sublayer and just above it in the inner region, this is the inner region, what do we have? We have almost a linear relationship with von Kármán constant. So K might be on here 0.41 here. So it just goes K times Utah, your friction velocity, times Y. So that means near the wall, your eddy viscosity just increases almost linearly, and then it kind of flattens out the top to a maximum value and falls down. So this is a typical type of measurement. We'll return to this figure later. Let's look at the second figure. This one's length scale, right? And this one, again, is the same coordinate system, right? So this is y, that's the distance from the wall, normalized by the boundary layer thickness. And this was our first approximation. L goes as K kappa times y, and that's really true near the wall in the inner region. What's interesting here is then you can see it sort of flattens out. So the very first models were just done sort of on this hand waving, much like I sat up here in front of the class. I can imagine Prandtl students were sitting around a chalkboard hand waving about what they think the length scales of turbulent flows would be away from the wall. But you can see in these original models, they're good near the wall where stress matters if you're trying to predict drag, but throughout most of the boundary layers, it's nearly a constant. So the next step to make a better length scale closure for models for prediction would be to try to modify these basic models. So let's go back and look at the arguments that led to these linear approximations. So in these figures, I'll just write down my findings. I say from 0 to say y over delta to about, I don't know, 0.15, the eddy viscosity, which we called epsilon m here, and mixing length L, we'll just say they go approximately as y over delta, right? So linear. And they have max values near 0.2 y over delta. And that's not a coincidence because that's where your maximum mixing occurs in that general inner, close to the wall, inner layer location in turbulent boundary layer. Okay, so this is one of your linear models, and this should, excuse me, this is an error. Let me rewrite it. I saw it and I was like, oh no, this is kappa, right? Times Utah, according to the figure too, and this is y. So this is linear, and L would just go as kappa times y, or if you normalize by delta, it's fine. And I already mentioned that this would be found experimentally by these early authors by measurements in the turbulent boundary layer in the wall and be about 0.41. So that's fantastic. Now you see when we get away from that very near wall region, things change. But you can notice, like I showed in the second figure down there, that L over delta goes that is about a constant outside this inner region right here. So we'll just write this as the inner region. And out here, this is like an outer region. And of course, there's a length scale, so I would assume if we go way down here, it goes something like this, down to like some atmospheric turbulent length scale, whatever that might be. If it's a low turbulence wind tunnel, it should go to be a very small value. Okay. And here, there's also a constant, which is just found experimentally. Okay. Now, when you get outside this boundary layer near the outer part of the flow, you'll get to the free stream. And when I say free stream, what do I mean? I mean, that's just the flow outside the turbulent boundary layer. It might be governed by, say, the nonlinear potential flow equations. But in that region between the edge of the turbulent boundary layer and the free stream, there's something that's intermittent. And part of the reason that these relations break down in the outer part of a turbulent boundary layer is because of intermittency. And we'll just say intermittency is gamma. That's how we'll kind of call it. So intermittency, or gamma, is some fraction, let's say maybe of time, in which the flow is turbulent. So how would I do that? Maybe I would take a hot wire and put it at the edge of my boundary layer and look at the time history of the velocity, and I would see what? I would see my chaotic motions, and it would go back to being like a nice laminar flow and back to chaotic motions. And so that would be a value between, say, 0 and 1. And that's what's really trying to be illustrated here up in this figure in 3.15. This is also from the famous work of Klebanov. You can see a theme here. It's a really important paper. He had a boundary layer edge of 50 feet per second. And once again, this is really before the age of digital computers in the lab. And this, each little ticks here is delta 1 second. And he, I believe, made something like a hot wire type measurement. And he got instantaneous velocity u. So here's y over delta. So this is at 0.4. So if this is the boundary layer, right? This is a wall. And so this is a y over delta equals 1. That's this location. And 0.4 would be here, right? So that's in the inner region. That's where kind of like these original scaling laws of how large the turbulence scales are from the wall, right? That's only for 40% of the boundary layer. You can see it's pretty much always turbulent. Like if I look at the time history here, it's always turbulent. And now let's just get away from the wall. So now I go down to maybe 60%, and that still looks like mostly turbulent, but then say that's 80%, y over delta 80%. And we're very close to having a mean velocity of the edge velocity, or the mean flow velocity, the free stream velocity, excuse me, it's 98%. And now look, now we only have like little turbulent motions every so often. And so if I looked at like this location, I would say these green lines represent turbulent motions, and maybe the orange ones represent, oh man, I'm gonna color this in, right? Sort of like laminar type motions. There's no turbulent fluctuations really. As I go away from the boundary layer, these little areas of turbulence decrease and decrease. These are happening in about 1 to 2 seconds, and then down here we only have maybe one little time where we're turbulent. So the intermittency is what? It's going down to 0 as you progress outside the boundary layer. And you can see in these early theories of von Kármán and Prandtl, they weren't even really aware or appreciative that intermittency even existed. And if they did, they would look at as like, well, it's not very practical, or have an inability to try to include intermittency in the theory. And this really happened through the 1940s. In fact, in the 1960s and 70s was when really intermittency was included in a lot of these predictions. Now, this just doesn't happen in boundary layers. It happens a lot of places. For example, ocean waves. You might think of like a rogue wave, and some people even are dismissive of the idea of rogue waves, that there's some highly chaotic, extreme blow-up event, and it has a very low intermittency. Or it might happen in, say, free shear layers, like an exhaust from a rocket engine. Really, you can probably think of almost any boundary layer, or turbulent flow where there's going to be intermittency and strange events happening between like a free stream and the turbulent flow itself. So this is something that really characterized turbulent flows and kind of throws away, some of these early simplified theories. And, oh, okay, excuse me. I wrote here from the paper, it's oscilloscope readings of U prime. So I'm not sure exactly how what like device they actually got on there with. But they were trying to estimate these factors of gamma or intermittency away from the wall. Okay, a few other notes. So, and these are just sort of writing what I've mentioned. It's that in the outer region of the boundary layer, y over delta is greater than 0.4. And there's, of course, larger and larger times of gamma, which is the intermittency. And we can divide the outer layer into two parts. There's sort of the free stream part, and there's sort of a inner part, if you will, some crossover region. And there might be something called, some people refer this as like a Reynolds number mixing length region. I don't see many people using it that way. Reynolds number mixing length region. And as your Reynolds numbers go higher and higher, then this intermittency region should be kind of like pushed out to the edge of the boundary layer. So for especially low Reynolds number flows, you won't see that occurring as much. So immediately you might say, well, we can make an empirical correction to our simple length scale model, right? So the simple algebraic or one equation type closure, which is the length scale type model, we say, okay, there's intermittency, and we're seeing the length scale flatten out. It's no longer just linear. What are we going to do? Well, I'm just going to make an empirical function to fit the data, and I'll use that in my CFD model. So that's what equation 3.20 should look like. I'll say as long as the flow is higher Reynolds number, there's some sort of distribution of the length scale, and here's our little empirical function. So if we just drop higher order terms, then we can just say, okay, L is kind of going as a constant, like some constant from the wall, or excuse me, the pipe diameter, if we're in a pipe flow. And you can write L this way. So we're going to return to that in just a second. Now I want to talk about a new figure, 316. I think it might be down here. Here it is. So this is also from this paper, Klebanov. Intermittency distribution across the turbulent boundary layer at zero pressure gradient. That's partial P, partial X bar equals 0. And they've used 3 different techniques, which aren't too important, but what is important is the data collapses. And they created a function, empirical function that fit this data. Here's y over delta, that's the distance from the wall, and there's intermittency, and should vary from generally 0 to 1. You can see experimentally there's some amount of error, because by definition, you can see here, this is greater than 1. Right, so oh no, that's, you can kind of gain some insight in the experimental error there. But once again, flow is fully turbulent here. And of course, this is the boundary layer edge. This is where UE would be looked at. And he fitted an error function. And we'll show this equation in a few seconds. So a few notes about intermittency. These factors measured and modeled by a lot of people. And one is, of course, Klebanov, where maybe original author, but another one was Corson. Stanley Corson, 1954 paper, very well-known researcher. In fact, the American Physical Society gives the Stanley Corson Award for young researchers, for those of you who go to a career in fluid dynamics. Maybe you would be fortunate to get the Stanley Corson Award from the APS for excellence in research. Anyway, so we have some maybe new empirical factor L for how it might vary for larger y. And we have also need to, we have some kind of model for the intermittency. We might need to try and make a new modification of the eddy viscosity. So we need to correct epsilon m for gamma, right? So typically, if gamma is 1 everywhere, it's turbulent everywhere, we don't have to worry about, or there's no intermittence anymore, so we don't have to worry about things. Okay, so let's look at one possible model. And you might say that the eddy viscosity goes as maybe alpha, which is a constant. It's nice to have constants, and a lot of people in the modeling business like to add them, so they have something to calibrate. And it might go as something as the friction velocity times maybe the boundary layer thickness. Now, we write epsilon m because maybe this is the modified eddy viscosity in the outer region. Okay, and if you make this type of model, which is the kind of original type of simple algebraic model formed for how eddy viscosity varies in the outer layer intermittent region, you'll find these are the relative values of the constant. So what can we do? We can try and use these new lengthen velocity scales, which we can derive from eddy viscosity and the length scale directly, of course, to try and normalize the eddy viscosity, which we showed in figure 3.13, right? It increases linearly and levels off. And we also have some other length scales to work with. So we might try and take equation 3.22, and I'm just going to, that was a little error, sorry. And we can also write them in this form, which is just a different form, not too important. And I also mentioned, and we're going to come back and use these in a few minutes, but I also mentioned that there can be some sort of function for intermittency, and one person named Nikosadze, I really killed his name, and a student in publication 1935. And this is that error function I was talking about for the intermittency, for incompressible turbulent boundary layer, right, with partial p, partial x is 0. And there's the error function. And for those of you who don't remember the error function, it's just 2 over square root of pi from 0 to, say, well, we just put in the argument, whatever that is. We'll just say it's x of e to negative x squared dx, something like that. And they'll evaluate to a value, of course. So x can be negative or positive. But anyway, there's our error function definition. And this would need to be integrated by, usually engineers would use tables, or now today computer program. So we're going to come back to this model and this model for L in a few minutes to recover some important results. But I do want to note some quick points here, that in all these early experiments, they show that the core pipe flow and the distribution of the eddy viscosity, epsilon m, will resemble the distribution of the fully turbulent portions of the outer boundary layer flow. So that's one point I wanted to make. And you can see a second major takeaway, of course, is the eddy viscosity increases linearly, then flattens out. And that's especially true in a pipe flow. which is what someone like von Kármán was looking at originally. So there's the pipe flow, there's the walls. And if we have a velocity profile, well, it's going to look like this. And there's our velocity profile in the pipe. And one more little graph. Make this green, I guess. This would be like a U, and then the second graph would be epsilon 2. And in both these cases, you have almost a linear distribution. Well, excuse me, in the eddy viscosity model, you have a linear distribution if you graph it, and this distribution here for velocity, it goes as U plus, goes as Y plus in the inner coordinates, and we'll recover that result in a second. So let's keep going here. There's my intermittency plot, and just to cover things, I don't think I mentioned this one, I should have. This is, let's see here, a length scale with pipe radius and distance from the wall with the middle of the pipe, right? Pipe radius, so this is the center of the pipe. I wanted to show this graph and discuss it too. I guess I referenced it here, but I didn't talk about the figure, excuse me. You can see near the wall, almost for increasing Reynolds number, we're actually getting lower integral scales in center of pipe, and that's actually totally non-intuitive. But you see that these Reynolds numbers are extremely small. The smallest one is 4 times 10 to the third. It's higher than the critical Reynolds number, certainly, of the flow, but it's a very low Reynolds number flow. And what happens when you increase the Reynolds number, right? So you would think that high Reynolds number flow, you would have independent or self-similar flows. And if you thought that, you'd be correct, because now here's the same type of flow, exact same type of flow, but now we have higher Reynolds numbers. See, this is 105 times 10 to the third. This is only 4 times 10 to the third, so you're looking at 2 orders of magnitude higher. And in this case, all these different Reynolds numbers have collapsed along one curve. Near the wall, right, we have a linear relationship. And far from the wall in this region, it's all collapsed, but it's, of course, non-linear now. And you can see why this chose this empirical function using, like, squares and fourth powers for an empirical function of, like, L over Y or L over R naught in this case. And all the data fits that. So if we keep increasing Reynolds number, it's still fully turbulent, and we wouldn't expect to see the turbulent statistics changing at all. So it's a really interesting observation. To me, one of the big takeaways is many of the theories apply really to high Reynolds number turbulence. Right, so if you're close to a transitional flow or even low Reynolds number turbulence, then you can expect to find self-similar turbulent statistics in your flow. If it doesn't matter if it's a pipe or a boundulaire, a jet, wake, backward-facing step, whatever, even more complicated flows like wings. And then, well, a reasonable person would say, well, what's low Reynolds number and what's high Reynolds number? And it's always going to be problem dependent. Low Reynolds number and high Reynolds number for a pipe flow is very different than, say, low Reynolds number and high Reynolds number maybe for like a jet flow or flow over a cylinder or a boundulaire. But in each case, you can assume that you want high Reynolds number, right? So much greater than 1. So the viscous forces are dominated except near the wall. One other graph. This is eddy viscosity in a pipe. So once again, here's eddy viscosity, here's Y over R, and there you can fit many models. You can see sometimes in these data there's a little bit higher eddy viscosity near in the region of maximum mixing, just like we saw before. Okay. So what I think we're going to do is we'll take maybe, I don't know, 5 or, let's see here. It's a little bit before the usual time, but that's okay because I think it's better to break into sections. So maybe we take like we'll just come back at 12:30 exactly, and then we'll do the second set of notes as the second part of the class, okay? Thank you.